1, booster ignition, and lift.
Have you ever wondered about how the world works and how we, for example, can note that the sun weighs nearly 2 times 10 raised to 30 kilograms, or why the apple falls down to the ground instead of up to the sky? Well, so did our ancestors. The idea of understanding the world has probably been in the minds of humans all throughout the history, but it was not until ancient Greece that the understanding of physics was implemented to determine laws of nature. It all started with curiosity and a will to determine and decide how the world functions. Ancient Greeks came up with theories and laws that gave origin to later discoveries. After plentiful revelations, there weren't many milestones reached, partly due to the reign of the Church. Not until about 1,000 years later did people question the theories of the Church, which gave rise to a whole new set of discoveries. 1600. William Gilbert claims that the Earth works as a magnet. 1638. Galileo Galilei makes a number of contributions to the evolution of modern science. Mid-1600s. Isaac Newton publishes an assortment of literary work, including the principle of gravitation and movement laws. 1799. Alessandro Volta invents the battery. 1821. Michael Faraday discovers electromagnetic waves, and a year later George Ohm realizes the connection between voltage and current, known as Ohm's law. 1904. Albert Einstein laid the foundation for all things concerning the theory of relativity, and ever since then the unraveling of the mysteries of the universe and evolution of our knowledge has flourished. Even though major discoveries have been made throughout the last centuries, all the scientists had to begin with their research from somewhere, as do we by looking into the fundamental laws of physics and trying to comprehend how the most simple everyday actions depend on laws of physics. Let's start with gravitation. Every object in the universe attracts everything around it with something called the gravitational force. For example, the Earth attracts everything in its surrounding space, but did you know that even the tiniest particles on Earth obey under the same laws? They do, but because of the ratio of masses between the objects, the gravitational force is insignificant, and the attraction doesn't create a movement of any object in question. Because the Earth is so much bigger than any object on it, all objects react relatively the same way to Earth's gravity. Also, the gravitational force is different in different areas on Earth. For example, in Sweden it is 9.82 and in the US 9.81. The lowest value is 9.78 and the highest is 9.83. It is denoted G. In our examples we will use the value of 9.81. The apple falling from the tree is a great example that shows how forces work on matter on Earth. When something is raised above the Earth's surface, it obtains a kind of potential energy. Just like the spring that is stretched will return back to its original state, so will the apple by falling to the ground. The equation for deciding the potential energy of an object at x height above the ground is mass times the gravity of the Earth times height. As we said before, G can differ depending on where you are on Earth, and also that we will use the value of 9.81 in our examples. An apple is hanging on a branch 10 meters above the ground. The apple weighs 0.2 kilos. Now let's put the values in the equation to calculate the potential energy of the apple. 0.2 kilos times 9.81 times 10 meters equals 19.62 Newton. The moment the apple begins to fall down to the ground, the potential energy starts to turn into kinetic energy, and the moment before it hits the ground, all its potential energy has turned into kinetic energy. That means that the equation for potential energy equals the equation for kinetic energy. M times G times H equals M times V squared divided by 2, where V equals the velocity of the apple falling down. We will come back later about kinetic energy. Now we'll explain something that is also vital to understand day-to-day physics, which is friction. We neglect air resistance because of its complex nature, but it is important not to do the same with friction between solid objects. When two objects are in contact with each other, the friction between them has a certain value that depends on the surfaces of the object. That value is called coefficient of friction. A higher value gives more friction, which means it will need more force to drag a certain object through a certain surface. You could say that the higher the value, the rougher the surface is. As always, it is easier to explain using an example. Let us say we have a box consisting of wood that weighs 4 kilos standing on a metal surface. While the box is not in motion, the coefficient for these two surfaces is 0.60. When we give the box a slight push, it stands still because the frictional force holds back the force from the push. If we push the box harder, the frictional force will grow, but at some point it will be fully developed, so it cannot grow anymore. At that point, the box will start moving if the force from the push is increased. So let's see how much force is needed to make the box move. The force of friction equals the coefficient of the material's surfaces times the normal force, which in this case is the same as the box's weight 4 kilos times the gravity of the earth 9.81. When the object is standing still, we will use the friction coefficient that's in play when the surfaces are static, meaning they are standing still. So F equals 0.60 times 4 kilos times 9.81. Here we can see that we will need a force bigger than 23.544 Newton to get the box moving. Later, when the box is moving, we can see with how much force the friction is fighting against us. The coefficient is the only thing that changes. Now F equals 0.42 times 4 kilos times 9.81. Here we can see that the force of friction, which is opposite to our pushing force, is 16.5 Newton. For instance, if we push the box with a force of 20 Newton, the actual force from the push is 20 Newton minus 16.5 Newton, which means that the box is moving forward by the force of 3.5 Newton. Remember that you can always go back in the video to check out anything that you might have missed. We will now explain kinetic energy by returning to the apple. As we said before, the potential energy equals the kinetic energy right before the apple hits the ground. By knowing this, we can determine a lot of factors using the formula mv squared divided by 2 and m times g times h. Like for example, we can calculate the velocity of the apple falling down or the mass of the apple. Since kinetic energy depends on the velocity of the object, the energy may vary as the velocity changes. Consequently, two objects with a huge difference between their masses may obtain the same amount of kinetic energy if the right velocity is gained. As an example, we will calculate the speed that a normal-sized car must come up to in order to obtain as much kinetic energy as a bullet. A regular bullet weighs about 0.01 kilos and has a starting velocity of approximately 300 meters per second. We neglect the changing of the bullet's speed as it slows down at the end of its course. When we put the values in the equation, we will calculate the bullet's kinetic energy. 0.01 times 300 squared divided by 2 equals 450 joules. So the bullet obtains kinetic energy of 450 joules. Now if the car shall have the same amount of kinetic energy as the bullet, it has to go with a certain speed, which we'll now calculate. We assume that the car weighs 2000 kilos. Now we just have to extract v to find out the value of the needed velocity. So v equals the root of 2 times 450 joule divided by 2000 kilos, which equals approximately 0.67 meters per second. We can now say that the needed speed the car must have in order to obtain as much kinetic energy as the bullet is approximately 0.67 meters per second, or 2.412 kilometers per hour, which is very slow for a car. The speed is very low because the mass of the car is much bigger than the mass of the bullet, but by this we have proved that it is possible for two very different objects to obtain the same amount of energy. This was all we had to show you for now. Thank you for watching and we hope you have learned something.